Hi everyone, I'm Dinesh Joshi, and I'll be speaking to you about boosting Apache Cassandra's performance using Netty. How many of you here have heard of Apache Cassandra? Okay, about half the room. For those of you who don't know what Apache Cassandra is, it is a distributed database which is massively scalable. And it's used by over 1,500 companies all over the globe. It's used by some of the very top recognizable brand names in the industry. Cassandra's website has a bunch of information about it. People have stored over 100 petabytes of data in Cassandra in multiple clusters. So with that said, a little bit about me. I'm a senior software engineer. I'm also a Cassandra committer. And I did my master's in computer science with a focus in distributed systems and databases from Georgia Tech, Atlanta, not too far from here. So we have a lot to cover, so I'm hoping to use 25 minutes for the talk. If you have questions, you can see me after, and I'm sure many of you might have questions for it. So one of the things that we face in this industry, especially around storage systems, is data trends. So this is the graph. I hope everybody can see this. But this is the graph of our data growth in the industry, and maybe it's not very visible, but the unit of measurement here is zettabytes. Zettabytes is, 1 zettabyte is 1,000 petabyte. And in 2019, we are expected to create about 40 zettabytes of data in the whole planet. Like all of us together as a human race will probably create 40 zettabytes of data just in 2019. Regardless of the actual figures, the trend is massively increasing because of IoT and other devices that we have. And more and more people are adopting data as their product itself. So data is the new oil in our industry. In addition to that, data is also becoming more critical. So, imagine if your medical records are stored in a database and it's offline. You can't pull a prescription, you can't verify what medication this person is on or is allergic to, right? So data has become more critical, and we have to ensure that data is always available. And with the explosion of data growth and the criticality of this data, we need to ensure that our systems can scale to meet the challenge, right? So Cassandra, being a distributed database, has to change in order to keep up with the times. But before we see that, what is Apache Cassandra and why is it so popular, right? It is a massively scalable database. There are publicly quoted numbers you can see on Cassandra's website. A bunch of people like Facebook, Uber, Instagram, Netflix, a bunch of them actually make use of Cassandra to store mission-critical data. It's written in Java, so it's very approachable. The code base is very approachable because it's written in Java. And it's a NoSQL database. It's not a traditional RDBMS. It's highly available and partition tolerant, which means what Cassandra does is it is eventually consistent. So although the database may not have absolute consistency, like strong consistency, asset consistency, like the RDBMSs, but the database is available, which means that your data will be available to you 24/7, right? But that doesn't mean that Cassandra is not consistent. It will still give you consistent responses. It's just that the nodes behind the scenes will reconcile the data differences eventually. It was originally developed at Facebook, and it's based on Amazon's DynamoDB paper, or Dynamo paper, and also Google's Bigtable paper. So these two concepts are applied in Cassandra by Facebook, and they created Cassandra, which is kind of a hybrid between Dynamo and Bigtable. So what we observed in Cassandra is Cassandra can scale. It can scale quite well, but it needs to scale further, as we have seen, right? And to understand where Cassandra falls short, we need to see how its scaling characteristics are. So in a distributed database, you obviously have a bunch of machines that are acting together as a single cluster storing data. So this is like a throughput versus cluster size graph. You can also do data storage versus cluster size kind of a graph. And on the x-axis, you see the number of nodes, and on the y-axis, you see the throughput of the cluster. And what you see is, initially, Cassandra will scale linearly, so you'll see a nice 45-degree angle. But as you increase the nodes, the throughput starts tapering off, and eventually it stops. So at this particular point, it stops scaling anymore. So you add more hardware, and you won't see any more returns on your investment in terms of the throughput in the cluster. And that is approximately 1,000 nodes. Now, for most companies, this would not be a big deal, or rather, your node count will be 100, 200, 500, right? But some of the big names in the industry can't live with just 1,000 nodes. You need to go beyond 1,000 nodes. And you need to do it reliably. So why does Cassandra stop scaling at 1,000 nodes? The primary reason is because Cassandra on every node runs a JVM in which you run the database instance. And JVM has a finite number of resources that are available to allocate. Now, if you look at the JVM, it's the code that runs are two major modules. One is the networking subsystem, because the cluster has to talk to all the nodes, right? And the other subsystem is the storage subsystem, which is the subsystem that manages the storage on the individual node on that particular host. And as you increase the node count, what ends up happening is the networking subsystem becomes very costly, and as a result, the speed with which you can store and retrieve data becomes less. Imagine if you had a room full of people, just two people are talking in the room, it's very easy to communicate with the other person, but now add 1,000 people in this room, and they're all talking to each other, it becomes impossible for you to understand what the other person's saying or communicate to the other person. And that's essentially what happens here. We have too many things inside that JVM. So what are these networking costs, and why is it so expensive? The number one cost is the number of threads, because Apache Cassandra, prior to the current release that we are working on, uses a thread per socket, and it uses blocking I/O to talk to all the nodes within the cluster. Externally, it uses async I/O to talk to the clients, but within the cluster, it uses blocking I/O. So the number of threads, the number of context switches, the thread signaling cost, and memory pressure and synchronization costs are very high, right? Also, the number of sockets that Cassandra has to maintain and keep open to all the nodes in the cluster. So imagine each process having to maintain 1,000 sockets. If you don't understand what all of these costs are, understand that blocking I/O is expensive when you have to talk to a lot of nodes within the cluster. One such example is, and maybe you guys would not be able to see this, but a thread context switch is very expensive within a CPU. And this infographic shows the number of instructions it takes for the CPU to actually do a certain instruction, execute a certain instruction. It's a log scale graph. And like a simple add operation takes less than one instruction. So you can actually execute multiple add operations in one CPU cycle. But the thread context switch cost, which is at the very bottom, is very expensive. And it's about 10,000 or 100,000 to 1,000,000 instruction cycles that it takes to execute that one thread context switch. Now, imagine if you have thousands of threads running inside a CPU, you will have to pay a very heavy cost of just switching threads. So in 4.0, we have introduced the concept of a event loop using Netty. Netty is a async I/O library that we use for networking. And what that evented loop does is it is just asynchronous. So it's waiting for I/O events to come in, and then what it does is it handles the I/O event and it moves on to the next event. And here, channels are a specific terminology that we use, which is a Netty terminology, but all it means is a client. So a few threads can actually service a bunch of clients, whereas in the earlier model, we had one thread dedicated to serving one client in Cassandra. And here client refers to the other node that it is trying to talk to. So the gist of this is, by switching to Netty, we have reduced the number of threads. That is the massive cost inside the JVM, right? And it's now proportional to the number of CPU cores. So it always makes sense to have few threads, but doing things asynchronously rather than doing in a blocking fashion, especially when it comes to any sort of I/O bound activities. Then Netty also allows us to use JNI bindings for EPOL and KQ. And EPOL and KQ are the native networking async I/O mechanisms on Linux and BSD, respectively. And JNI bindings are much more performant than what JDK has for NIO. And we also make use of the JNI bindings for OpenSSL, which speeds up the encryption. And at the end of the deck, I have some actual figures to share with you. So the other major cost within Cassandra is streaming, because as I said, it's a distributed system, and it has a mechanism to exchange data between the two nodes. And this is one of the other big expenses within Cassandra. Whenever a node is either replaced, or it has to be repaired, or there is some sort of range movement. Range movement is a very specific Cassandra operation to transfer data between two nodes, right? When that happens, streaming kicks in, and streaming slows everything down. And the reason that happens is because in pre-4.0 is the old version of Cassandra that exists, meaning Cassandra 2, Cassandra 3. Cassandra 4 is the new version that we are currently working on. And so imagine two hosts want to send data between each other. And the blocks that you see here are the records. They're called partitions within Cassandra. And the green things are data files that hold them. So now host B doesn't have any data, host A has data, and it needs to send data from host A to host B. You allocate some memory. Then these partitions or the records are actually read into memory and deserialized, or rather serialized on the wire. And then they are transported over the network on the other side, where they are deserialized and reified into Java objects. And when you create too many Java objects very quickly, it causes a lot of garbage collection on both the sides, right? And then eventually, this host is going to write that data onto disk. So this is how data exchange worked between two nodes prior to 4.0. But in 4.0, we found opportunities to actually make use of zero-copy semantics. So the Linux kernel and most major operating systems allow you to directly transfer data from the disk to the network without involving the CPU, and it's called zero-copy APIs. And so we are making use of zero-copy APIs that Netty has exposed. And so what it allows us to do is, in a situation where we want to transfer the whole file or data file from one host to another host, we just zero-copy it to the network, and from the network back onto the host that is receiving. So this actually speeds up the data transfer quite significantly, because we don't really have to involve the CPU, no garbage collection kicks in, nothing of that sort happens, right? And you'll see the impact of this relative to the previous versions of Cassandra. So this was a test that our friends at Netflix ran on Cassandra 4.0, which is on the trunk right now. The release has not been cut. But on the x-axis, you see different AWS instance types that they used for conducting the performance test. And what they did is they loaded up 6 terabytes of data, 500 GB of data on each host. And essentially, they terminated a host, and they tried to bring it back up. In that event, Cassandra has to recover from the remaining nodes in the cluster. And so in 4.0, which is the blue line, which is the trunk, right? You see that it takes about 25 minutes, and it is quite linear in the sense like it's quite stable. Irrespective of the size of the instance that you're using, you basically are going to see the same kind of performance because you're not involving the CPU as in the older version of Cassandra. So in the older version of Cassandra, you will take up to 2 hours to recover a host which has 500 GB of data. While in 4.0, which is the next version, you will see about 22 to 25 minutes of recovery time. And it all depends on how much bandwidth you have on your host, right? So this is essentially the amount of improvement that you see. So you see about 4 to 5x improvement, and this is still on trunk. It's not yet cut. We are still testing this in the community. So this is a major improvement that Cassandra has had. The other improvement that we've done is encryption. So in Cassandra 4.0, we make use of Netty quite generously, and a lot of people, like Cassandra always had encryption between nodes, and also it had encryption from the client to the server. But it has to be scalable, right? To be practical, it has to be scalable. So earlier, we used to make use of the SSL engine, which is the JDK SSL engine, which ships with the JDK out of the box. And you can see from a perspective of the number of requests per second, as well as from the raw number of bytes it can transfer, the improvement is massive. It's about 4 times the improvement, it's 4 times the improvement. And so the point is like now you can actually enable encryption without really slowing down the entire cluster. And this is important as well from a business perspective because data security is important. Even if it is within the data center, it is important to encrypt your data between nodes. So in summary, what I can say is that we've measured the number of the amount of latency that 4.0 has with pre 4.0. It's an improvement of 40% on an average and about 60% lower on P99, which is the 99th percentile. And this is on a baseline of couple milliseconds. So it's not like Cassandra used to take 10 seconds to respond. It used to always respond, like if you design your schema the right way, it'll take a couple milliseconds to respond if you give it the right hardware. And on that baseline, we have seen about 40% to 60% improvement on P99s. Memory efficiency, it's 10 times more efficient. It's just by mere virtue of removing all the threads that we use for internode networking, it's 10 times more efficient. The internode encryption, which is the encryption that you use for nodes talking to each other internally, it's, as you can see, it has had 4 times the throughput. And overall, the database has about 2x the throughput of 3.0, which is the older version of Cassandra, right? So with that, I guess Cassandra 4.0 is turning out to be a really solid release for the community, and a lot of big like contributors are contributing in performance improvements because, as you saw, the data growth being one of the big driving factors, as well as the recent security breaches that we have seen in the industry, right? So you want to make sure that you are able to encrypt, but encryption should not come at a massive cost as well. So that's pretty much it from me. I guess we sort of covered it within the time allocated. Yes?
How did you get to Netty instead of not NIFI?
Sorry, not?
NIFI?
So I think it was just a practical consideration. Netty already existed in the database. We already made use of Netty. So if you were connecting to Cassandra as a application, right? We always used Netty for that communication because you could have like 1 million containers talking to the server, right? And you don't really want to blow your stack or heap as a result. So Netty already existed in Cassandra. What we didn't have is Netty being used on the back end of Cassandra, where it would talk to other nodes within the cluster. That was still blocking I/O. The non-blocking part was only on the front end, where you would talk to the application. So I think Netty pre-existed NiFi. Any other questions?
I was just reading online, but just to confirm, the whole Spectre meltdown disaster didn't really affect performance more than 5 to 10%. Is that what you? Because, or what was your? That's what it says online. I want to hear what you because they had to change the microcode and all that.
Yes. So I think the fallout of Spectre is still happening. It's not like it's done. But yes, in some situations you could see about even 20% regression in performance on the CPU side itself. Yeah, I'm a performance geek, so so this was very interesting. Yeah, it totally depends on your workload. Yeah, go ahead.
How are you managing the state of a request in progress through the Netty events? Like, is there something that's keeping track of all the requests that are being passed through the Netty event loop?
Yes, so that already existed within Cassandra, because irrespective of whether you're using blocking I/O or non-blocking I/O, that client state already existed within Cassandra. It's just that now the way you interact with it is in a more asynchronous manner. So it's not perfect. It's still going through changes. So like it's still evolving, I would say. Yeah.
When you're talking about the new way that you transmit data, are you trying to say send file to kernel API?
Basically, yes. But the thing is, it still has to honor the throughput that you set in the configuration. So even if you want to do send file, which goes as fast as you can, you don't want to starve the client's actual applications of bandwidth, because you're sending files to a node that is recovering, right? So we do something which is a hybrid approach. We still do kind of send file, but we also throttle it if you have set some throttling limits. If you have not set any throttling limits, we are going to go as fast as we can. Yes?
Are the previous versions and 4.0 network compatible with each other?
Yes.
Upgrade one node, one Cassandra node of 1,000 to 4 and have it keep running?
Yes. So with Cassandra, that is the whole philosophy. You need to be on the previous major version. So you can be, I think, on 3.0 or 3.11. Those are the two main versions that Cassandra community supports. And you can upgrade your cluster one by one. So there's zero downtime for you, essentially. Yes, go ahead.
The way that you're doing the connections and the way that you rewrote the connections with the threading models looks very similar to the way HTTPD did it with the different MDMs like events and not before but simple order. Have you given any thought to making this pluggable to address different use cases? Not you, the community.
Yes. That frankly has not yet come up in the discussions. The amount of work that had to go in, and it's still, as I said, it's still work in progress. These are our initial benchmarks. So adding a more pluggable way of doing the connection management is going to be something that we probably will take up next. There are bigger problems to solve in Cassandra, I would say, from the perspective of operators as well as users. And the community is not that big, I would say, that can support all these concurrent projects. Any other questions? Cool. I think we're done. Thank you.